Hello, welcome to our lesson today on strict method of slab analysis. So today we are going to continue from where we stopped in part 2. So this is actually going to be part 3 of it. And in today's lesson, we are going to look at slab that have fixed or continuous edges. Fixed edge or continuity. So far, what we have been dealing with has been slab that are simply supported all around. And in practice, we rarely meet such slab. So most of the slab we will meet in practice are those ones that have either one or two fixed edges or continuity. So let's go into the lesson. Now, the strict method of slab analysis, it allows a certain range of flexibility between the span moment and support moment. And so there's a little limit of flexibility because of the plastic rotation capacity of reinforced concrete slabs. Considerably arbitrary readjustment on the ratio of the span moment and the support moment can be comfortably made. So let's look at this figure. If you look at this figure, this is typical of the beam a strip load we've been having in this strip analysis of slab, where you have the sides are loaded with continuous UDL and you have a large range of the midspan unloaded. So if you draw the bending moment diagram, you're going likely to have something like this. Let's assume this is a moment in the left support and this is a moment on the right support. Now from analysis here, we will come back to this. It shows that the sum of the absolute value of the positive span moment and negative end moment at the left or the right end, shown as ML or MR in that figure, depends only on the conditions at the respective ends and is numerically equal to the negative moment if the strip carries the load as a cantilever. What it means is that if you have this is a span moment, the sum of the span moment and either the right support moment at the right or support moment of the left will be equal to, if you will have moment, assuming you have this beam and you cut it at the middle and treat one side as a cantilever load. So if you treat it as a cantilever load, the load that you will have will be the sum of the span moment plus the support moment. If you were dealing with a cantilever at the right, so it will give you the sum of the span moment plus the support moment at the right support. And so if we are dealing on the left, it will be likewise. So what it therefore means that in determining moment for design, one calculates the cantilever moment, select the span moment, and determine the corresponding support moment. Please take note of this. First of all, you calculate the cantilever moment. The cantilever moment, I said, is like cutting this beam and allowing the load to act as a cantilever at the support. So if you calculate the moment due to that load, that is what is termed as cantilever moment. So if you calculate the cantilever moment and then you select the span moment and determine the corresponding support moment, because once you select the span moment, the support moment will now be the cantilever moment minus the span moment. You get more clarification when we start working on example. So Hillerbock noted as a general rule for fixed or continuous edges that the support moment should be between 1.5 to 2.5 times the span moment in the same strip. Usually the support moment is higher than the span moment. So he suggested that the ratio between 1.5 to 2.5 should be used. He said that higher values should be chosen for longitudinal strips that are largely unloaded. In such cases, say between 3 to 4, the ratio of between 3 to 4 might be chosen. So now let's look at this. This is a figure, a rectangular slab, similar to what we handle when we look at rectangular slab. But the only difference is that in this slab, you have this side is continuous, this side is continuous, while the opposite side is simply supported. This opposite side is also simply supported. And so that brings a level of continuity into the slab and makes it different from the other one that was simply supported all around. So in those ones, we only handle span moment, but in this one, because there is continuity at each, we will be talking of support moment also. So if you look at let me make it bigger. If you look at this slide, it's similar to the rectangular slab. We handle this short side is labeled B and the long side is labeled A. And so if you look at, let's start with the load distribution. The load distribution is the same as we did in rectangular slab. At the corners, you have a value of Q over 2, Q over 2 at each of the 4 corners. At this place, the value, you have a value of Q. At this place, you have a load of Q. At this entire middle strip in the XY direction, you have a load of Q acting across the whole span. And so now let's look at the dimensioning. If you look at the dimensioning, let's say in the short span direction, the middle portion is still B over 2, like we had in a rectangular slab. But to make take into consideration the stiffness due to the continuous edge, the strip at the continuous edge is usually bigger than the strip at the opposite end, which is simply supported, because this fixity, this continuity, give the slab a certain level of a higher stiffness at that side. So that is why we introduce this concept, this value alpha. And so alpha usually have a value less than 0.5. And so when you do 1 minus alpha at this edge, you use alpha at the other edge. So this is alpha p over 2, 1 minus alpha p over 2. Since alpha is usually less than 0.5, so what you will have here, 1 minus alpha is usually going to be higher than alpha. So because of that, you're going to have a bigger strip on the continuous edge and a smaller strip on the other side that is simply supported. These things happen when you have two opposite edges with different conditions. That is, the other side is continuous while the opposite side is simply supported. In a situation where the two opposite sides are simply supported, alpha does not come in. In a situation where the two opposite sides are fixed, alpha will not come in. So if you go to the long edge, you're only going to see the middle side is A minus B over 2, but at the edge, the continuous edge, you will have 1 minus alpha B over 2. At the simply supported edge, you will have alpha B over 2. And so with that, you have this slab to work with. If you take section, let's say section AA, and the long edge, and this is, where is AA? This is what you're going to have. This is the load you're going to have. This is the bend. You're going to have this support moment, which if you calculate, this is what you will have. You're going to have this span moment. If you take moments at BB, that is at this middle edge, middle strip in this direction, this is what you're going to have. And because you have a load across the entire span, and one side is continuous, one side is simply supported. This is how the bending moment will look like. There's a support moment here. There is no support moment here. There's only span moment. So the support moment, if you work it out, it will be something like this, and the span moment will be something like this. But take note of this distance. The distance between the simple support and where you have the maximum span moment is given by alpha b. Take note of that. We will need that. I think when we are solving example, you will understand this figure better. So you have explained all these things. I've explained all these things. So the maximum, these are the calculation by taking strip, which are when we do examples, you will understand better. So the maximum positive moment in the x direction that the middle strip is given by this. If you sit down, you can work them out, just taking moment like we did in other examples. And the cantilever moment is like this. So therefore, the negative moment is going to be the cantilever moment minus the span moment. So that will give you the support moment. So from the moment equation so far, the ratio of the negative to positive moment in the x direction is given. Take note of this equation 1. So the ratio of the support moment to span moment equals to 1 minus 2 alpha all over alpha squared. They derive this from the equations. You can sit down and do it on your own. But take note of this. You might need to memorize this equation. That is the ratio of the support moment to span moment equals to 1 minus 2 alpha all over alpha squared. This equation is usually used to solve for the value of alpha. So it is reasonable to choose the same ratio between the support and span moment in both the y direction and x direction. So I've mentioned about this alpha b. So these are the value maximum positive moment in y direction, just calculate what we have been doing. If you apply same day, you have the support moment in the y direction as this. And so with the above expression, all the moments in the slab can be determined once a suitable value of alpha is chosen. We usually calculate alpha. From that equation 1, the equation I said you should know, can be confirmed that the value of alpha from 0.35 to 0.39 give corresponding ratios of negative to positive span moment of 2.45 to 1.45, and this is a range that is recommended by A level. So usually a good value of alpha should be between 0.35 and 0.39. That is okay, so take note of that. So that when you calculate the value of your alpha, you will know if you're right or wrong. And so that takes us to exercise 3, which we are going to solve together. The question says a 175 thick reinforced concrete slab is 9 meter by 6 meter and carries a total surface variable action of 4 kN per meter square. The slab is continuous in two adjacent edges and simply supported at the other two adjacent edges, assuming the support moments are 1.75 times the span moment in all the strip in x and y directions, and using the strip method, determine the moments at all the critical points in the slab. Take unit weight of concrete. Unit weight of slab as 25 kilonewton per meter cube. I think this should be unit weight of concrete. Take load due to partition and finishing as 1.0 kilonewton per meter square. So we are going to solve this exercise 3 as we continue. So this is the solution to our exercise 3. So if you look here, you will notice that we have this is the slab. The slab we told is 9 meter by 6 meter. So A is 9 and B is 6. So let's go to the dimensioning first on the short span, which is the y direction. The middle one is usually B over 2, so 6 over 2 is 3. That's why we have 3 meters here. This one, because this is the simply supported edge, is usually alpha B over 2, and B over 2 is 3, so that's why we have 3 alpha here. this one, the H strip at the continuous H is usually 1 minus alpha B over 2. So B over 2 is 3. So we have 3 into 1 minus alpha. So when we go to the long span direction, the middle strip is usually A minus B over 2. So B over 2 is 3. So A is 9. So 9 minus 3. That is why we have 6 meter here. And this H, because this is continuous, we have 3 into 1 minus alpha, like we had in the short span. And we have 3 alpha here. So that with that we have dimensions. Our slab, what we need to do is to find the value of alpha so that we know the actual dimensions of this at the H strip. A load distribution is usually like a rectangular slab. So we have, let me say, Q over 2, Q over 2. At the corners, we all have Q over 2 in both directions. And this place is Q in the horizontal direction. This place is the same thing here. But this middle strip in the Y direction, you continue Q acting across the entire short span. So let's calculate the value of alpha. The simplest way to calculate the value of alpha is to use that equation 1, which I advise you to memorize. The equation says that the ratio of the span of the support moment, that is negative support moment, to this positive span moment is usually 1 minus 2 alpha all over alpha squared. And in the question, we were told that that ratio is 1.75. We were told to take the ratio of support to span moment to be 1.75. That means you can equate this equation. You can equate this 1 minus 2 alpha all over alpha squared, equate it to 1.75. And if you rearrange it, it will give you this quadratic equation. 1.75 alpha squared plus 2 alpha minus 1 equals to 0. This is derived from this equation. And you go ahead and solve your quadratic equation with whatever method you're comfortable with. And so when you solve, usually take note, because it is quadratic equation, you're going to have two values. It is you that is going to use the things we have learned you to know which value is right. For instance, in this exercise, alpha was 0.376. And remember, I told you that the real alpha should usually be between 0.35 to 0.39. So usually sometimes you have two values of alpha because it is quadratic equation. One could be greater than one or negative or whatever, but one of them, if you're doing things right, will always give you a value between 0.35 and 0.39, which is the right answer. And I will advise you to always keep the value of alpha in 3 decimal places. That will help the accuracy of your work. So when we now have the value of alpha, we can now know that 3 alpha that we have in a dimension is 1.128, and 3 into 1 minus alpha is 1.872. So we can now know that this place 3 alpha is 1.128. 3 into 1 minus alpha is 1.872. So with that, we know the actual dimensions of our slab in the H strip and middle strip. The next thing is to calculate the value of Q. We were given enough information to calculate the Q, which is the design load on this slab. We were told that the thickness of slab is 175 mm, which is 0.175 meter. The unit weight of concrete is 25 kilonewton per meter cube. So the weight of slab is going to be multiplying the thickness of slab by the unit weight of concrete. That gives us 4.375 kilonewton per meter cube or square. This is going to be per meter square. You can put that. Now, due to partition and finishing, we were told is 1.0 kilonewton per meter square. So you can add the two. This weight of slab and the load due to partition. That will give us our characteristics permanent action GK as what? 5.375 kilonewton per meter square. And we were told that our characteristics variable action, our QK, is 4.0 kilonewton per meter square. So we can use our design load formula that shows that 1 Q is what? 1.35 GK plus 1.5 QK, where 1.35 is a factor of safety for permanent action and 1.5 is a factor of safety for variable action. And so with that, we calculate our value of Q to be 13.26. So after calculating the value of Q and the value of alpha, the next thing is to go and calculate the moment in each of the strips and in each of the direction. So first of all, we go into the x direction H strip. What happened to the x direction H strip? This is the x direction. This is the x direction. This is the H strip. So if you're moving across this, you will have here Q over 2. You won't have any load here, then Q over 2. So we can now go and look at it. The x direction, that's why we have this diagram. Q over 2 here, Q over 2 here, no load here, then Q over 2 here. So what we now have to do will be to calculate the moment. So first of all, we calculate the cantilever moment. The cantilever moment is what we are going to calculate for now. Okay, sorry, we were looking at the wrong diagram. This is the right one. So this is our diagram, Q over 2 and Q over 2 here. So this is the side that was 3 into 1 minus alpha, which is now 1.872. This is the side that was 3 alpha, which is now 1.128. So we calculate the cantilever moment. The cantilever moment is calculated by going to the continuous edge, that is a fixed edge if you want to call it so. Go to the continuous edge and take moment to that side. So this is a continuous edge. This left side is a continuous edge. This side is simply supported. So we take the cantilever moment. Please take note of this. We take the cantilever moment at the continuous edge. So this is what we do. We come here. This moment is a UDL Q over 2. If we change it to a point load, it will now be Q over 2 multiplied by 1.872, which is this Q over 2 multiplied by 1.872. So that gives us the magnitude of the point load, and the point load is going to be placed at the middle of the load and at the middle of the load, such that the distance between where it is placed and where we are taking moment is going to be 1.872 over 2. So that is why we have this 1.872 over 2. And you know moment is force time distance. So if you multiply the 2 and take into consideration the value of Q, you will have this 11.62 kilonewton meter, which is a cantilever moment. The next thing is for us to do this maximum span moment. The maximum span moment will be done by taking moment on the simply supported edge. We take moment at the simply supported edge. So we go to this simply supported edge. We have a load of Q over 2 and it's acting on a span of 1.128. So what we do, maximum span moment is, if we change this to point load, it's going to be Q over 2 multiplied by 1.128. And then we also going to multiply it a distance of 1.128 over 2. So that's why you have Q over 2 into 1.128 squared over 2. And if you work it out, it's 4.22 kilonewton meter. And once that is done, to get the support moment is going to be the cantilever moment, which is 11.62, minus the maximum span moment, which is 4.22. And if you work that out, it's 7.40 kilonewton meter. And so by so doing, we have been able to calculate the support moment and the span moment in the H strip in the X direction. So the next thing is to go to the middle strip in the X direction. Let's go to the diagram again. This is the middle strip in the X direction. So you have Q here, you have no load here, you have Q here. So similarly, we now have Q here, no load here, Q here. The distance is 1.872 and 1.128. So we are doing the same way. Calculate the cantilever moment. So when we calculate the cantilever moment, is Q multiplied by 1.872 is Q multiplied by 1.872 multiplied by 1.872 over 2. So that's why we have 1.872 squared over 2 multiplied by Q. So by so doing, we had our cantilever moment to be 23.23. And if we calculate the span moment that same way, we have 8.42. To get the support moment, we subtract the maximum span moment from the cantilever moment, and that gave us 14.79. So we also go to the y direction middle strip. So let's go back to the diagram. This is the y direction. And in the middle strip of the y direction, what we have is a load of Q acting across the whole span. So this is what we do. This is what we have. The y direction, is it? Oh, sorry, I went to the wrong one again. The y direction middle strip. So you have the load of Q acting across the whole short span. You have the continuous H at the left and the simply supported H at the right. And remember, I told you that the distance from the maximum span moment to the simple support H is usually B alpha, and B was 6 here. So this place is 6 alpha. That means the remaining one will now be 6 minus 6 alpha. So what is the value of alpha? Alpha was 0.376. So that means 6 alpha is 2.256 and 6 minus 6 alpha is 3.744. These values are important because it marks where you're going to take the division between what you're using as a cantilever moment and what you're using as a maximum span moment. So what we now do is that at this demarcation, whatever is in this side will be part of the cantilever moment. Whatever in this side in this will be part of the maximum span moment. So we can go ahead and calculate. We can go ahead and do the calculation. So in that case, the cantilever moment will now be, because the distance was 6 minus 6 alpha is 3.744. If you follow that pattern we have established, will now be 3.744 squared all over 2 multiplied by Q, and that gives us 92.94. So maximum span moment will now be using the other distance, which is 6 alpha, and it's 2.256. So you have 2.256 squared over 2 multiplied by Q. That will give us the maximum span moment. And of course, the support moment will now be the cantilever moment minus the maximum span moment. And that gives us 59.2. And so if you go to the X strip in the Y direction, it will be the same as the X strip in the X direction. In that case, you have our span moment to be 4.72 and the support moment to be 7.42 kilonewton, the same as a strip in the Y direction. So that is the solution to our exercise 3. In our next video, we are going to look at exercise 4. Thank you for watching up to this